Morning, everyone. My name is Achin Gupta. I work for the Architecture and Technology Group in Arm for a team that's responsible for software standards for the Arm system architecture. Today, I'll be talking about virtualization extensions that have been added to the secure state in Arm v8.4. I have with me my colleague Jean-Paul Etienne. We are working on this project together, and would be happy to take any questions at the end of the presentation. So getting started, so the introduction of virtualization extensions in the secure world is kind of the step in the evolution of TrustZone. TrustZone itself was introduced back in 2003 in Arm v6k and enabled system-wide partitioning of resources between the secure world and the normal world. So what this enabled was that you could create a trusted execution environment that was distinct from the general purpose operating system. And in this trusted execution environment with trusted boot and a trusted OS, you could provide the properties of integrity and confidentiality to trusted apps. Now, these trusted apps, they ran on top of trusted OSs, and they in turn could provide security services to the normal world, the security services being authentication, crypto, integrity management, and such. And the software stack looked a bit like this, where the trusted OS pretty much occupied the entire secure world. It ran in the privileged modes that we had back then, monitor mode, system, hierarchy, FIQ. The trusted applications ran in the user mode, the client applications in normal world in EL0, and there was a trusted OS driver running in the operating system kernel. So this was all good. It served us well for a number of years. But then as time progressed, there was a need to provision platform management functions or firmware services as well on the system. And since the secure world was entirely occupied by the trusted OS and the normal world was the general purpose operating system, there was no real place for putting all this platform specific code. So when Arm v8 came along, we added a separate exception level called EL3, which had its own translation regime. And this enabled binary separation. So the trusted OS image could be pushed into secure EL1 and secure EL0. And the EL3 exception level was available for instantiating platform services. And these platform management functions were mainly like power management and errata management, SIP services, OEM services, and such. So now that we had EL3, we could do some standardization, and we wrote some specs. For example, the SMC calling convention spec, which lays down the ground rules for invoking any firmware service. On top of that, there's a power state coordination interface spec. There is the software delegated exception interface spec, which provides a mechanism for injecting NMIs into the operating system. To support the specs, we started the Arm Trusted Firmware project that provided the reference implementation for these specs and also a reference implementation for trusted boot. And the software stack looked something like this. So on the normal world, the trusted OS bits were pretty much the same. If there was a hypervisor, then we would need a trusted OS driver sitting in the hypervisor as well. But EL3 firmware, it had a combination of platform-specific code provided by the SIPs. There was a trusted OS. There's a trusted OS dispatcher that's responsible for communicating with the trusted OS, which is entirely in secure EL1 and secure EL0. So again, this was fine for a while, but what's happening now is that the size of the code base in the secure world is increasing. It's becoming bigger and diverse. In EL3, firmware components are being provisioned by a variety of vendors. So again, there's the generic code, but on top of that, SIPs, OEMs, and such. The number of functions that are expected, that's increasing. And there's no way to isolate these components from each other. So if one component provided by one vendor has an issue, has a bug, then that can compromise the entire EL3, which being the most privileged exception level in the system, would not be a nice thing. In Secure EL1, what we are seeing is a requirement from SIPs and OEMs for multi-tenancy, where multi-tenancy basically means you need to run multiple trusted OSs together. The main reason behind that being OEMs want to ship their devices with a rich set of applications, trusted applications. And a trusted application is written against a particular trusted OS. And either it's not desirable or trivial to take a trusted application written against one trusted OS and port it to another trusted OS. So it's basically not very portable. On the other hand, the other thing is that certain SIPs have their own trusted OSs, and they say that the drivers that are available to access the secure peripherals, they would be packaged in this trusted OS. So now if there's another trusted OS that needs to sit alongside, it has to talk the language of the SIP's trusted OS, which would be in the form of a communication interface exported by the SIP's trusted OS, right? So that leads to a kind of a integration problem where all these trusted OSs have to kind of understand the other component's language, which is not great. And then in the normal world, like in this diagram, there's a trusted OS driver with its own interface to talk to the next exception level. With multiple trusted OSs, you would need multiple such drivers, each talking their own language. Right, so the idea is that there needs to be isolation between these components that are being provided by various vendors. And on the ARM v8.3 architecture, it's not really possible. It's not possible to apply the principle of least privilege, where one component can only see what it absolutely needs to ensure its correct operation. And that's because EL3 and Secure EL1 have the same view of the physical address space and interrupts. So essentially, all these components have to play nicely with each other rather than making some assumptions about the isolation properties. So it's not possible to isolate EL3 firmware from trusted OS. It's not possible to isolate components within EL3 firmware from each other. It's not possible to isolate two trusted OSs from each other. And then the other angle to the problem is that in the past, there have been privilege escalation attacks where the normal world's been compromised through the trusted OS, because the normal world can now not be protected from the trusted OS itself, right? So as a result of this, as I said, like, since all the components have to play along nicely, this makes auditing and certification quite difficult because they all have to implicitly trust each other. The other aspect is, because of standard interface at the component boundaries, as I said, like, each component is talking its own language, right? The integration and interoperability of these software components becomes very difficult. So what we need is hardware-enforced isolation. So what that means is restricting access to the physical address space and registers from processors and DMA-capable peripherals. And once we have this isolation, once a component knows that it can access only this part of the address space and these devices, then there's no need for mutual trust, and it would make it possible to audit that component separately. And then we need a software architecture so that these components can talk a common language for the most common things that they do to communicate with each other. And that would enable the vendors to work together better and just promote generalization of code. More importantly, it would enable removal of trusted OS specific code from exception levels where it's not really required, where it's not adding a lot of value. So in 8.4, we added virtualization support. So the processor has a new exception level called Secure EL2. All the features of EL2 are mirrored in the secure world as well. And this enables the hypervisor to control the visibility of physical memory from a virtual machine, the usual stuff. The ARM system MMU architecture gets an upgrade as well, and there would be support for secure stage 2 translations, right? And this further enables isolation at the level of DMA-capable masters. And then finally, the gig architecture will add support for the virtual gig in the secure state. So at the hardware level, these are the changes to enforce isolation. And this solves the problem of EL3 from secure EL1, normal world software from secure EL1, and isolation of distinct software components. But we still have the problem of vendor-specific code for that interoperability and communication, right? So what we are saying is that why not have a architecture, a software architecture, which basically takes the existing secure, non-secure software stack and just generalizes the most common things that are done, like message passing between the trusted OS driver in the normal world and the trusted OS, memory sharing, because is there really a need for differentiation at this level? And in a world with virtualization, since resources will be tied to a particular component, there needs to be a mechanism for sharing these resources as well between the various components. So that's what this framework or this architecture should provide. So some of the standard building blocks of this software architecture are, one is a secure partition, which is essentially a virtual machine with an isolated address space to access only the resources that it needs. And it can be used to host a trusted OS. It could be used to host a driver stack for a secure peripheral. And it can continue to expose secure services to the normal world and to other secure partitions that might need it. Now, each secure partition or the secure VM would need to specify what it needs for correct operation. So in the system address space, these are the memory regions, these are the devices. So it can specify that through a concept of a resource description, which is essentially a manifest, which has a list of these memory regions, these devices, these interrupts, right? And then finally, we have the secure partition manager, which consumes the resource description, make sure that the request from a particular secure partition is valid, the dependencies are met, and it is responsible for initializing and enforcing this isolation at runtime. So it can be, in the simple words, it can be thought of as a partitioning hypervisor, a very minimal partitioning hypervisor. And this replaces the need for the trusted OS specific dispatchers in secure firmware. So it's like one component that manages all communication with the trusted OS VMs, with the trusted OS secure partitions. And at runtime, the other role that it fulfills is that all the requests coming in from the normal world, they need to be ferried to the right trusted OS VM, and the responses have to be sent back to the normal world, so it takes care of that as well. So if we take these three components, the world starts to look a bit like this. You have the normal world, which is protected from the boxes on the right-hand side, where you have a secure partition with one trusted OS. There's another secure partition with SIP drivers. That's just an example. That could very well be a SIP provided trusted OS as well. Each is running it in its own sandbox. Inside secure EL2, there's a secure partition manager that relies on the resource description to create that isolation. So that gets us a bit far. But to ensure that interoperability, there needs to be some kind of a glue that binds these building blocks together. So the crux of the work that we are doing is specifying two documents. One is the secure partition client interface, and the other one is the secure partition runtime, where the client interface is essentially a set of ABIs or SMC calls that generalize message passing and memory sharing between a client and a secure partition, which would be a trusted OS. And what this enables us to do is that it's only the endpoints that need to understand the trusted OS specific communication and the intermediate exception levels through which the messages pass. They can just have a generic driver which is responsible for sending the communication on its way in either direction. So essentially, what that means is SMC-based transport for vendor-specific drivers. So the SMC transport does not interpret the contents of the messages. It's only responsible for getting them from point A to point B, and that promotes generalization. So that's one specification. The other one is secure partition runtime, and this describes the relationship between a secure partition and the secure partition manager. So in terms of if the secure partition provides a resource description, what should be the contents of the resource description to make sure that the secure partition manager is able to enforce that isolation. On top of that, as I said, the secure partition manager is responsible for sending requests, receiving responses. So how does that happen? That requires, because the partition manager and the secure partitions are operating at different exception levels, so that needs an interface as well, so it specifies that interface. And finally, it's responsible for initializing each partition. So if we add these specs to the previous diagram, it starts to look a bit like this, where the TrustedOS driver in the operating system kernel, instead of having its own set of proprietary secure monitor calls to talk to the TrustedOS, it can rely on a generic SPCI driver. The hypervisor, instead of having TrustedOS specific driver again, can have a generic driver which can just forward the communication in either direction. The TrustedOS secure partition and the other secure partition can talk to the secure partition manager using SPRT, right? And the secure partition manager relies on the resource description to be able to enforce the isolation properties. So what this enables is that the amount of vendor-specific code that was required earlier in secure firmware, that gets minimized, and we are able to push it into a separate partition of its own. So in terms of the work that we are doing, the spec status, we wrote a white paper, and this presentation is more or less based upon that white paper. So that's available on TrustZone. The SPCI spec, it's Alpha 1. It's still in its early stages. It's available on the Arm TrustZone, and the SPRT Alpha spec is under development, and we should have that out, the first version out by October, by next month, basically. Now, all this is well and good. The crux of these specifications, like most of the time that we are spending right now, is on finding out what's the impact on trusted OSs as a result of this generalization that we're introducing. So like any physical OS, trusted OSs also make certain assumptions. So they make assumptions about how memory is shared with the normal world. So typically, the normal world driver would allocate a page, pass the physical address. The physical address is received by the trusted OS. It maps it in its translation regime, and that's not a problem. Trusted OSs assume access to physical interrupts. So they use that to implement critical sections. Whenever the normal world issues a blocking call or a fast call, it runs with interrupts disabled. So that assumption's there. And above all, there's this concept of a controlled exit, where what that means is that you're running in a trusted OS, and if an interrupt for the normal world arrives, the trusted OS gets dibs on it first. It takes that interrupt, does not acknowledge it, does not do any management of that interrupt, but uses that invocation to park its state and then go back to the normal world, right? So the main thing is virtualization invalidates these assumptions. So the question that we're asking is, can a trusted OS run in a VM just like a general purpose or rich OS runs in a VM under the control of the hypervisor? So all these assumptions that are there in a trusted OS, how serious are they? Like, what's the gap between turning a trusted OS into something which is suitable for running inside a virtual machine, right? And some of the high-level consequences are that the secure partition manager would now constrain access to the physical address map. Now, if you're sharing memory, then the trusted OS will see the intermediate physical address space instead of physical address space, so all memory sharing has to be done in cooperation with this SPM. Since there are multiple translation regimes involved now, the memory attributes used to map this shared memory, they have to be consistent across all these translation regimes. And regarding the GIC, a trusted OS can no longer mask normal world interrupts. It cannot mask physical secure interrupts, right? So the runtime model that it assumes, due to this assumption that it has access to the physical resources in the system, whether that will scale to running inside a virtual machine or not, that's kind of the crux of the problem. And then finally, this SPM replaces the dispatcher for dispatching the request to the SP and obtaining responses. On the normal world side, the expected impact is that, as I said, the trusted OS driver can now use the SPCI interface, the SPCI specification provided interfaces to do message passing and memory sharing, right? So the proprietary SMC communication can be replaced by SPCI, and then hypervisors can implement a generic SPCI driver instead of to ferry communication between the guest VMs and the trusted OSs, instead of having trusted OS specific drivers instantiated in them. So that was kind of the high-level overview of what's happening in the trusted OS world. But there's more to the work that we have been doing. And there's also the concept of secure EL0 partitions. That this kind of predates the work that we're doing on secure EL1 partitions. And the motivation behind this is that in some market segments, like enterprise and data centers, we saw that trusted OS adoption is virtually non-existent, right? And in these market segments, there is a reliance on firmware or BIOS to provide services. The services are pretty much the same, like you have management-related services like error handling, RAS error handling, and BMC communication, or security-related services like access to secure storage and such. Now, all these services have to be instantiated somewhere, and this brings us back to the original argument in the earlier slide. Now, one option is that you offload these services to a separate controller, but that approach is not universal, it's not ubiquitous. So there has to be some mechanism for instantiating these services on the AP. And again, to ease the auditing process and to separate the liability, there has to be some kind of isolation. So now, since trusted OS adoption is not a concern over here, secure EL1 is a kind of an empty exception level. So what we did was that on Arm v8.3 and earlier, to achieve that isolation, we leveraged secure EL0 as the exception level. It's like, let the secure firmware take ownership of secure EL1. All it has is a shim which can relay communication originating from the partition into the EL3 firmware and vice versa. But the secure partition manager fulfills the same role for enforcing isolation, but it sits inside EL3 firmware instead of secure EL2 because it's not there. And yeah, like even in the absence of virtualization, we can achieve a certain level of isolation through just the secure EL0 exception level. And this is good enough to satisfy use cases like authenticated variable storage, capsule update, RAS error handling, BMC communication, right? And the specs that I spoke about, SPCI and SPRT, they cover this aspect of the software architecture as well. So the components can continue speaking the same language, right? And whether you're on a system that's v8.3 or in the future it would be v8.4. One caveat is that in these partitions, in the absence of system MMU support for stage 2 translations, if you have a DMA-capable master, then it can still cause trouble. But for specific use cases, secure EL0 partitions can still be used. Now, as a precursor to this work, there's something else that we did, which is known as the management mode secure EL0 partitions. So in the UEFI.org has the platform initialization spec, So version 1.6 introduces the concept of standalone management mode. Now, this was introduced to kind of circumvent some of the problems with the traditional management mode, where there was sharing of data between normal execution and management mode, and that led to a lot of vulnerabilities that most of us are aware of. So they introduced the concept of a standalone management mode, which would be a self-contained software stack with absolutely no dependence on any external entity for getting the work done that's requested. So what we did was basically took this UEFI image, which had the standalone management mode drivers, and placed that into a secure EL0 partition as a first step. And this is, so on a system that uses UEFI, you'll have two images. You'll have a normal world UEFI image. You will have a secure world UEFI image in the secure partition. And we wrote a spec, which was the communication interface. It has one SMC that can be used to request services from this partition. The interface between the secure partition and the secure partition manager is Arm trusted firmware specific at the moment, but this is what will evolve into SPRT, as I showed in the previous slide. And yeah, the secure partition manager manages this one partition. This code's been upstreamed. The EDK changes have been lined up for upstreaming, and it's able to fulfill use cases like RAS, variable storage, and I think later in the day there are talks around this specifically. So that's kind of the gist of the work that we've been doing and what we are proposing. Any questions?
So have you tried to look at the performance implications?
Oh, sorry. Absolutely.
Another one. So have you tried to look at the performance implications here? Because, you know, currently it's kind of fast, switch over to little work, get back.
Not as yet. So
any estimations or?
None that I can provide right now. Because we are still working on virtual platforms. So yeah, we need to do some benchmarking on a real platform to do that. Yeah.
So, no, it works. Are you, I had to totally take notes on all the abbreviations. Are you planning to support SCPI or SCMI over SPCI? And this is actually a genuine question. I mean, either of the two are basically system management protocols that allow you to change whole system components that really need to be abstracted away in the ARM world. We currently live in a world which is just insane in that regard.
Yeah, so first of all, we do have some favorite alphabets that we keep reusing. So we have PSCI, SPCI, SCPI, so on and so forth. But there are discussions around providing an SMC-based transport for SCMI. Mm-hmm. And one of the things that we're considering is whether the SPCI interface can be leveraged for that instead of introducing another set of SMCs mm-hmm. to fulfill that use case.
That sounds like a really good idea. How far out do you think this is?
We began discussions before the Connect. We're having discussions now, so Tanu, he's a colleague. He owns the SCMI spec. He's around with the Connect, so be happy to talk to him. And
so I would like to make sure we mandate that mechanism for future EBBR versions. For future EBBR versions, that's a presentation that's coming up
right
after right now behind that door. But basically, in the embedded world, we live in a state where every board vendor implements their own interfaces for which everything there is, from pin control over clock interfaces to anything.
Yes.
And that's totally hurting the ecosystem.
Yeah, so SCMI was like the first step towards generalizing that, and I think once we have the SMC-based transport available, that should complete the story. But yeah, we'll have the conversations with Grant and yeah.
All right, thanks.
So basically, one of the questions I have was, if you look at your previous pictures, it seems very, very natural to basically extend the SMC instruction, and since you're making 8.4 plus architecture, make the SMC instruction available to user space, EL0. Wouldn't that be nice? Because then all of a sudden, some of these paths become simpler. If user space can, in EL0 can make SMC calls, that would be really nice.
Yeah, well, not sure I can comment on that because it's kind of a core architectural thing. But yeah, there is an overhead in the shim in between, but we have to do some performance benchmarking to see how much of that overhead is.
Yeah, it isn't obvious why SMC wasn't originally allowed to be from EL0. I mean, I couldn't quite see why, but whatever.
Yeah, well, we had the SVC.
If you start allowing SMCs to be generated from EL0, you're breaking a lot of existing software, a lot. I mean, nothing expects that. The same way you can't do an HVC from EL0, that this is a privileged instruction. The right way to do it is to do an SVC, take you to your kernel, and then you're in privileged land. SMC is really not designed to go all the way up, and it would bypass your hypervisor, which is kind of a problem. You expect your hypervisor to do some level of sanitization there.
Kind of a tangential question based on your answers, so feel free to direct me to the right person. You mentioned someone responsible for SCMIS here. It'll be good if I can get to meet them in person. I don't know who that is.
Yep. So
the other one is, so the question was more on...
oh no, he had to fly out and come back in again, so
Okay.
he'll be here any moment.
So my question is on SCMI. I've seen some patches being posted to the Linux kernel. And one of the use cases for SCMI is to set the CPU frequency. And I saw that at least implementation and upstream submitted was using mailboxes and it's kind of making up a message and sending it across. That seems pretty heavy-handed for trying to switch CPU frequencies. I would prefer the latency be significantly smaller for those cases. So can some latency-sensitive parts of the SCMI be handled like a system register or something like something as common as setting the CPU frequency, having to go through a mailbox seems excessive. System register would be a lot better.
Right, so I'll forward this to Tanu, but I know that traditionally any communication with system controllers, the common approach is a mailbox and a doorbell mechanism, right? And that's what SCMI talks about as well. So in terms of the latency concerns you have, so yeah, I can forward you to.
I understand for general thing mailboxes looks good, but something so critical, it feels like a little excessive.
Right.
That's all. Thanks.
So from the architecture point of view, the resource are exclusively owned by one trusted application or can be shared by multiple trusted applications.
So first of all, it wouldn't be the trusted application, it would be the trusted OS, and that would provide the services to the trusted application. But yes, the idea is that with the changes in the SMMU, it should be possible to isolate a peripheral to a particular VM, right? Now, the question is, if other VMs need to access the same resource, then what happens, right? And then that's something that we are thinking about because there are a few models, like if it's possible to virtualize the device completely, like something, then you each could have its own virtual function. That's one way of doing it. I'm not sure how relevant would that be in the secure world. The other option is that, yes, this one VM owns the device and the others access that device through a paravirtualized interface, right? But that interface would be based on SPCI again, so it's a standard way of communication. Or the other thing is that, yeah, fine, maybe the SPM can take ownership of the device and everyone talks to the SPM instead of one VM taking ownership of it. So there are multiple models. There's no one single answer at the moment for this.
So for architectures before 8.4, so you mentioned these secure EL0 partitions. So do these partitions support secure interrupts?
They can be forwarded interrupts that belong to them, but being in secure EL0, they can't kind of access the gig or do anything in that regard. So some of the interfaces that we are specifying in SPRT are aimed at sending the interrupts across to the secure EL0 partition and obtaining a response, right? So, yeah.
Okay, thank you.
In your talk, you mentioned that you do not expect there to be any differentiation in the secure partition manager, and I guess that you will provide an example implementation through ARM or Linaro and expect everyone to use that. Whereas I think that I can imagine several ways to differentiate with the secure partition manager.
Yes.
For example, someone might want to reduce the number of lines of code running in the secure world, or someone needs some specific certification over there.
Right.
So how do you expect this to be handled? Will there be only one partition manager, or will it be possible to implement another one with the same interfaces?
I don't think there would be only one, because it's a separate exception level. So again, the whole point of binary separation comes into the picture. But that's again something that we are looking at. There'll definitely be a reference implementation from ARM, right? So some of the code that's already upstream, the secure partition manager, which caters for this use case, it's going to evolve into satisfying this use case and then moving on to satisfy the secure EL1 partition use cases. But having other secure partition managers, that's not completely off the table. As long as there is a contract between EL3 and secure EL2 that can be specified, a well-defined contract, that should be possible.
I have one more question.
Yep.
One of the answers again was that the devices, some of the shared devices could be moved to the SPM.
Right.
I'm sorry, secure partition manager, whatever it stands for, right?
Yep.
So wouldn't that kind of bring us back to square one, where they'll start implementing more stuff there, and now that becomes a new trust zone?
Well, you have a fair point that the SPM could have its own partition by the side, right? So instead of giving the ownership to, say, one trusted OS, the SPM can also, one of the intentions is that in the firmware, if we can minimize the amount of vendor-specific code and have it more generic so that it's easily certifiable and auditable. So instead of putting the driver inside secure EL2, it could be put in a separate partition that the SPM controls.
Sounds good. So that would probably be kind of delivered by the vendor.
Sorry?
So you expect that part to be delivered by the vendor or the platform owner, right?
Yes.
Okay.
All right. I finished early. That's good, I guess. Thank you very much.